Hello, good morning. I have a homework due on Wednesday. Homework 6, I had earlier said it will be due Wednesday, but I'm going to make it due on Friday. That's the day of the midterm itself. So that's, it was March 2. Okay. And remember, midterm 2 is on March 4th. Is that okay? Because the solutions will be out, so it should be okay. So just be responsible if you can. Whatever questions you can, finish it early so that you're not doing the homework at the last moment. What I can do is that this is a little flexible due date. By chance, you're not really having time to study for it, so you don't spend time working on the homework. So it can be due until the end of the day. So is that clear? Yeah, so a little flexible. And all the guidelines for the midterm 2 remain the same. Pretty much like midterm 1, concentrate on homework and lecture examples. That's what I suggest. And if you want more resources, go to the textbook, which is the central resource for the whole thing. Lectures and homework is the important one, that's the guideline, but the lectures are just a supplement in a sense for the textbook. Any general comments or anything you would like me to address here? Logistics wise. Okay. We are doing electrical circuits, and we almost we were in the verge of introducing a third component of electrical components. Broadly electrical circuits, but let me list this as electrical components. What builds up an electrical circuit, the fundamental entities here. One is the battery, and we have been using the symbol. So that these two horizontal lines represent wires. That's the positive side of the battery, that's the negative side of the battery. So that's positive, that's negative, and we have been using the symbol V for this. V also is a unit of voltage, so it serves as two purposes, but in the context it should be clear. We then introduced the idea of capacitor. Before that, I said battery basically is a reservoir of positive and negative charges. We are all talking about electric charges. These are the primary players in this game, if you want to call it. So you need a reservoir for it. So a battery is basically a reservoir or for that. Capacitor is a temporary reservoir. So it also is a reservoir, but it's a temporary reservoir, and it doesn't have a positive negative polarity on it unless you have a very high highly charged capacitor. Most of the capacitors don't have that polarity, and notice they're very similar property here. It is one is longer segment of line, and here you say capacitor is C. So this is the capacitance of a capacitor. And finally, we barely started introducing a resistor, and resistor will have the symbol as zigzag line, and the symbol for that would be R. This is measured in voltage. We use this in colloquial language these days. How many volts does your smartphone have? Like whenever we talk about how much percentage it is charged, we're talking in terms of voltage. This is capacitor. The unit is capacitance, and its unit is farad. And resistance will be measured in ohms. Either you say ohm or typically ohms. Right. So that's your three components, and we would like to introduce the third component and more, or we want to know the details of what this is. Very broadly speaking, this is a device, like these days we talk about, or devices connected to a power supply. So this is any device you can think of, or anything that uses up energy. Battery is a source of energy. Capacitor is a temporary reservoir of energy, and resistor is where you spend the energy. So that's what consumes the energy. So in that sense, in these days, whatever we talk about, so it's any device you can think of. And when we were talking about capacitor, we wanted to have connection between how much energy does it use up, and remember, voltage is voltage per unit charge is energy. So capacitance, we said, was related as Q over V. So we want to talk about how much energy. Actually, it is good to write it in terms of voltage. That's a so how much energy or energy per unit charge does a capacitor involve? So that's Q over C. So if C is large, for the same amount of charge, if C is large, then the energy stored is less. Same thing, we want to talk about resistor also. So the voltage V, which is a measure of how much energy it consumes, or how much energy per unit charge it will consume, will be I, the current times the resistance. And that involves two quantities, the current and resistance. So let's go ahead and define each of the quantities. So we began this last time. Oh, did I change the? No, I forgot. Come on. Okay, so this is, we should introduce current. Current is represented by the letter I, and it is charge per unit time. It's a flux of charge. So if you are in a path, you ask how many people are walking through that road. It doesn't matter whether it is going to the right or left. You take one direction as positive and the other direction is negative, and you give positive numbers to whoever is going to the right, negative numbers to whoever is going to the left, and a measure of how much is the resultant and movement will be your current. So current is charge per unit area. Sorry, per unit time. So that will be Coulomb over seconds. Let me change this. So that will be coulomb. The unit would be coulomb per second. And this again is such a common unit. You tend to use it so often that you create a vocabulary for it. You say this is ampere. So an ampere would be coulomb per second, right? Coulomb per second, and this is usually represented just by the letter A. So whenever you talk in terms of current, you say there is 5 amps of current, and you will, again, this is reasonably common to use this in a daily language. You would say, if you have a power supply, how much current can it provide? So it depends on how much load you have provided. Voltage is fixed, so how much load you provide decides how much current is pulled from the power supply. Usually the goal is the following. So you have a simplest electrical circuit consisting of a resistor. So you have a resistor or connected to a voltage or a battery V. A battery could be your power supply tube. And if this was fixed, typically this is fixed. You go to a market and you get a battery that has a fixed voltage. That means it has a fixed amount of energy whenever you take a certain amount of charge from that battery that is fixed. If this is fixed and this is also fixed, resistor is how much energy is it going to consume per unit charge. Let us say this was 50 ohms. And ohms has a symbol of a sigma, right? So you have, that's a Greek letter, you have 2 horizontal lines and a spherical structure in there. So that's ohms, right? So this is, I should say, this is ohms, right? That's farad, and that's the voltage. V. Again, V is fixed, R is fixed. That's the moment you connect a load or a device. This is a specific characteristic of the device. Voltage is the characteristic of a battery. How much, what is the variability or what is the response the device has to that voltage? And that's by the current, how much current it pulls. If this is voltage is very high and this is very small, then it will pull a lot of current because it doesn't have any resistance to that. So it will pull a lot of current. But if it is large, then it will not let too much energy flow through that, and I will be small. So the connection between V, I, and R is voltage across a resistor is equal to current times the resistance. So it's a linear relationship between the 3 quantities. This is so common, so this is so useful for our purposes that there is the law associated with it. So you say this is Ohm's law. Usually in physics, whenever you say it is a law, it means that it is a fundamental law. That means you really cannot change it based on it is usually not material dependent. But this is an unusual statement because this is pretty much empirical in the sense that it depends on the material. For different materials, it changes a little bit. It is not as perfect as it looks. What it means is that if you were to plot voltage on the y-axis and let's say current on the x-axis, then this will be a straight line. When I goes to 0, V goes to 0, so this will be a straight line going through the origin, and its slope will be off. That's what it's supposed to represent, but most of the times the materials do not function perfectly, so they deviate a little bit. This might go this way, that way. So this is not perfect. So this is empirical. but it has stuck that it is really a law, and it is, I should stress that this is actually an empirical law. Okay, so with that, so we have our three equations. So that V is equal to I times R, voltage across a capacitor is Q over C, and again we can do the same idea that we did earlier. If we have one resistor, this is what happens. If there are two resistors, what happens? There are three resistors, and so on. But before that, let me tell a few characteristics of this resistance R. And before that, I should just, as a simple exercise, calculate how much current is going through the resistance. All right. So I is equal to V over R. If it's a single resistor that is connected, the voltage across this resistor is exactly the same as the voltage of the battery that is connected to that, because these 2 points are metallic wires. The potential across these 2 points is the same as the potential difference across the battery. So that's equal to 10 volt here, and divided by the resistor, which is 50 ohms. So that's about 0.20 amps. So again, what happens in an electrical circuit? This is fixed, that's fixed. The moment you connect it, it is decided how much current flows through this circuit is decided by how much resistance you connect to that. So that's the response. That's what the system tries to do, given these 2 fixed quantities. So that's the way you want to think about it. Every time you connect an electrical circuit, what is the response is basically current. What happens to the currents? That's what typically it is. In a capacitor, it was how much charge collects on the plates. That's the response. In a resistor, it is how much current flows through the electrical circuit. That's the response. It's also good to understand what other quantities resistance depends on. So resistance these days, resistance is associated with the whole device that we have, but we can think of a very simple system. So resistance of a wire. The idea is that everything is built out of metallic components, and if you know the resistance of a single wire, you can actually add up and talk about the resistance of a whole device in a sense. So if you have a simple wire, resistance is about how much current, how much it resists the current. So if not for any resistance, all the current will flow through this device. If you think of it as a shorted current, all the charges, this is positive, negative, they will all come and come together and neutralize each other. But if there is a device, it will resist it. And what does it depend on? Resistance depends on how long it is. So resistance will be large if the length is large. So let's say rho L. So this is L is length. So if you have a wire and the wire is longer, the longer the wire, larger is the resistance. What else does it depend on? It is inversely proportional to the area. That's area, and A is area. Again, think of current as a flux of the movement of charges. And if you are in a corridor and you're walking and there are a lot of people around, if the corridor cross-sectional area was larger, then the resistance is less. If the corridors were very long and you have to cross the whole corridor, then it is proportional to the length, like how much resistance you face when you are walking through the corridor is proportional to the length, but it is inversely proportional to the area, in the sense if the corridor was wide enough, then you have many people can walk through it in an easy manner. So it is proportional to the length, inversely proportional to the area, and it depends on what kind of material it is. If it was a conductor, it is very easy for the charges to go through. If it is a dielectric material, it is not very easy to pass through. An insulator, for example. And that's captured in the material properties. So this is called the resistivity. So rho is the resistivity. And that's a material property. So material specific property. So if it was, for example, if you are choosing a copper wire versus a gold wire or an aluminum wire inside the electrical wiring in your house, how does that decide your electric bill? That's decided by this number, right? A certain material will have a higher resistance over another resistance, and you choose it accordingly. Sometimes it's a cost that comes as a parameter, and sometimes it is the efficiency of how much energy you really want to waste or use in the process. So now we have the properties that decides your resistance. In your homework, there is one or two problems related to resistivity and resistance. But broadly, what we want to do is that if you have an electrical circuit, if you have more than one resistance, as I said, there will be many resistors as in modern devices. We have typically in the order of millions, but we are talking in terms of one or two, the basic way in which they can be compounded together. So earlier we talked about capacitors in series and parallel. So now we talk about resistors in series and parallel, how we can combine them together. So let's talk about resistors in series to begin with. Resistors in series. And that would look like you have two resistors connected end to end. And it's connected to the same battery. Let's say that's R1, that's R2, and that's voltage V. So let's say that's 10 volts. Typically in the market, 9 volt is easier to get, but for calculation purposes, it's nice to keep 10 volt. R, let's say, is 100 ohms. It's relatively less amount of resistance, usually 500 and 1000 and even larger resistances are common, but let's keep 100 ohms for R1 and 200 ohms for R2. And of course, the idea is we want to ask how much current is pulled out of this battery, how much charge goes through this resistance per unit time. That's a measure of current. The main idea, current is a flux, and charges cannot be created or destroyed. So whatever comes in out of this battery has to go through this. It cannot be destroyed. So whatever goes in here has to come out here, and whatever comes out here has to go in here. So whatever is the number of charges that's going through R1 has to be the same as the number of charges that goes through R2. That's because charges cannot be created or destroyed in the system that we are talking about. So that means that whatever is the current I here, that's the same that goes in here. Let me call that I1, but that's the same as I, right? And it's the same current that goes through here. It's pretty much like a pipeline of water. If there is no source or sink in a pipeline, that means there is no leak or there is no input of water. Whatever goes on one side has to come out on the other side. So that's the idea here. That's I, the current that is pulled out of this battery, it has to be equal to I1 and I2. So the currents remain the same in both the resistance. And that's a statement of conservation of charge if you want that the batteries do not, the charges are not created or destroyed. So that's a concept there. But once we have that, we still have the property that whatever is the potential difference between these two polarities of the battery, that has to distribute along this. So this is at a high potential, low potential. This high potential shows up here. Right? Those 2 points are at the same potential because this is just a metallic wire. Metallic wire has the same potential across that. So that's a high potential. That's a low potential because that's connected to the battery. And that has to be distributed over that in a linear fashion. So if this was plus 10 volt and this was 0, and somewhere here in between, there has to be a 5, there has to be a 6, and so on. And this, if we say the potential difference is across a resistor, so that's V1. And across this resistor is V2. And whatever is that drop has to add up to the total voltage, exactly like we had in the case of capacitor. So we have V1 plus V2 is equal to V. These are very similar arguments we used in capacitor, but if you were to look into your capacitor nodes, it's exactly the opposite. In the case of capacitors, when they were in parallel, we had charges that were the same and the voltage distributed. So capacitors in parallel pretty much behave like resistors in series as far as the mathematics goes. Like conceptually, they're completely different things. You have on one side, you have collection of charges, and in here we have the movement of currents that's decided by that. But mathematically speaking, resistors in series is equivalent to capacitors in parallel. Okay, with that, so let's see what next you do. So we still have 2 equations, but there is not much information if you go in a concrete manner. So you have to do one more thing here. And you say that this is, we define what is called an equivalent resistor. So equivalent circuit. An equivalent circuit in this case is that instead of 2 resistors, you connect a single resistor. There's a single resistor connected to the same battery. And you ask, what should be that single resistor which pulls the same amount of current as the resistor, as the circuit with 2 resistors. So it has to pull out the same amount of current I. That's Req. So that's the description of the problem. And once you have that, you can actually go ahead and whichever is the distribution law, start with that. So you have V1 plus V2 is equal to V. And now use your equations to replace each of the voltage there. V1 is equal to I1 times R1. That was our defining relation for the resistance. That was your Ohm's law. And that is true locally. Like for each resistor, voltage across that resistor and the current that's going through the resistor. So that's the description. So V1 is equal to I1 times R1. V2 is I2 times R2. And the voltage V is the full resistance, and that's where the equivalent circuit comes in. This full circuit is equivalent to a single resistor. That means it is I times R, where it is R equivalent. If we use the fact that I1 is equal to I2 is equal to I, these 3 cancel out. And you learn that R equivalent is the sum of 2 resistors, or sum of the individual resistors. So given the 2 resistors, you know what is the effective resistance that's there in the whole circuit. And even though that may not be really relevant in the problem as to what exactly is the equivalent resistance, and immediately once you know this, it helps you determine what is the current that is flowing through the circuit and what is the individual currents I1 and I2, because both are the same. So let's talk about those questions. Let's say all these were equations. So if you want, you can memorize it, but it is good to deduce it for each problem, because very quickly you can compound this very easily. Voltage distributes, current is the same, and if you want resistance distribute, you don't say resistance distributes, resistance add up to an equivalent resistance. So let's calculate our equivalent. In this case is R1 plus R2, that's 100 plus 200, so that's 300 ohms. Right, that's your expression for R equivalent. And the moment you have R equivalent, you know that V is equal to I times R equivalent. That means 10 volts is equal to I times 300. And we can calculate I, which means we know I1 and I2 also, because they are identical. So I is equal to 300 divided by 10, so that's 30 amps. Which is a large amount of current. Typically, if you have 1 amp in your did I can do this correct? No, that's too large, right? This is wrong. So this should be opposite, right? So this is 10 divided by 300. So that's 1 over, so that's a 3 point, that's 0.33 milliamps. And that's typically the amount of current that actually goes through your circuits. If 1 amp, it happens in situations where you have a big device like a refrigerator or an air conditioner. So those are things that consume a lot of energy. Typically, an electronic device is very small. A computer does not even have a milliamp. It is significantly less than a milliamp. So a computer doesn't consume as much energy as, not even close to, as a microwave or a refrigerator or so on. Christian?
Yeah, so
yes.
That's 10 equals I times, what is that number?
That's 300, that came from here.
Oh, okay, thank you.
That's the R equivalent, so that's 300 ohms. Or maybe my handwriting, right? That's better. But if you say it, it's okay. Again, a milliamp is common. An electronic device like your smartphones and other things don't consume so much energy, so it is less than that. But whenever there is heat involved, that's a good way of looking at it. Heat is one of the places where we lose a lot of energy. If you want to maintain the temperature of this room, that's a lot of electrical energy being used. As far as your computer is not heating up too much, then you can expect that there won't be significant amount of drainage of power. Once you know current I, is also I1 is known and I2 is known. And it is good to then understand what is the voltage V1 and V2. We said V1 plus V2 is equal to 10 volt. What are the individual potential differences? Once we know the current, we can calculate that. So V1 is equal to I1 times R1. That's I1 now we know is 0.33 times R1, that's 100. So that's 330 ohms. So 330 volts. Again, there's something wrong. Oh, this was a milli, right? So this was into 10 raised to minus 3. Right? So that's 0.33 Help. So this was 33. What am I mixing up? 33. Did I do this correct? No. Okay. Okay. Yes. What did I do wrong? Okay. So 10 divided by 3 is 3.33 into 10 raised to minus 2. So 3 point, let me write that down. So that's 3.33 into 10 raised to minus 2. I want to put a minus 1, so that's 33 milliamps. Okay, good. And that's a slightly large amount of current. Thank you. Okay, so that's 33 milliamps, and this then becomes 33 into 10 raised to minus 3 into 100, and that's about 3.3 volts. How did I know that there was a mistake? I was earlier getting about 0.033, and I know that V1 plus V2 has to add up to 10 volts. So that's a small check you have, that these two voltages should add up to 10. Whatever number you have, you can check it that way. So if it was that small, I knew that it won't add up to 10. So V2 similarly is equal to I2 times R2. That's equal to I2 is the same as I1, so that's 33 into 10 raised to minus 3, this time multiplied by 200. So that's 6.6 volt, and to 2 sig digits, it is clear that 6.6 plus 3, that's about 9.9. So to 2 sig digits, this is 10 volt. You can always have the third digit is not there, so you don't know how much it is getting rounded off to. So it is, it can be 10 volt in that sense. So that's your voltage and currents. There is one more thing that you can use in resistors, and that is that how much power is consumed. Like that means to say that how much energy is consumed per unit time. In capacitors, we talked about how much energy is stored in a capacitor. That's a static situation where you have so much energy stored in a capacitor. But now we are talking about current charge per unit time. So that allows us to calculate how much energy is used per unit time. So that in 24 hours, if we multiply by the time, then we know how much total energy is consumed. So it's a common usage in electrical circuits is the idea of a power. So this is power consumed, and power is energy per unit time, and so this is power. So this would be equal to voltage. Remember, so this is current times voltage. Notice current is charge, so that's Q over T, right? And that's voltage. That's energy. That's time. So energy per unit time is what is defined as power. So that means not write it this way. So just for your information, this is energy per unit time. That leads to the idea of what's the unit of power. That will be joules per second. And that's a watt. And you might have come across this often again if you have seen your electric bill. Electric bill typically comes in the order of watts, but then how can you decide about energy, how much energy you have used when you're talking about watts? So you have to multiply by the time, right? So you would say you start with watt, and then you want to multiply by a time, but then you don't multiply by a second because you will get too big a number. So you multiply by an hour. So how much energy do you use per hour? And even that comes out to be too large. So often the unit that you use for your consumption of power is kilowatt hour. So this is often abbreviated as kilowatt hour. So that's just a unit of energy, because once you multiply the power by time, what is remaining is joules. So that's just a unit in terms of joules, but with a factor. So there is a kilo, and hour itself is in minutes and seconds. There are about 3,600 seconds. So how much is 1 kilowatt hour? So kilowatt hour is, kilo is 10 raised to 6. Watt is joule over second, and 1 hour is 3,600 seconds. So that's 3.6 into 10 raised to 9. 3.6 into 10 raised to 3 are already, oh sorry, that's already at 3. That's 10 raised to 6 joules. That's the unit in which your electric usage by an electric company is calculated. That means you at least use this much, right? It's very common for us to use this much of energy on a daily basis. So your bill comes in that. And then again, you have homework problems related to how, if your electric bill is so much in kilowatt hours, so how much joules of energy are you using? So it's basically a energy or a unit conversion problem. Since I talked about power, it's good to calculate how much power is being consumed by the first device or the first resistor, and how much power is being consumed by the second resistor. So P1 would be equal to multiply the two currents and voltages. So it's I1 times voltage P1. I1 we know is 33 milliamps. So that's 33 into 10 raised to minus 3 amps. And the voltage V1 was, we said 3.3 volts. So that's 33 into 3.3. So that's about 99. That's about 100, right? So 33 into 3 is 99. So 99 into 10 raised to minus 3 watts. 99 into 10 raised to minus 3 watts. And watts is simply abbreviated as W. What about the power P2? The same thing, you just change to I2 times P2. I2 is double of that, sorry, I2 is the same, but V2 is double of that. So this will be, this is 99, that will be 198. So that's 198 into 10 raised to minus 3 watts. Again, if we make this to 2 sig digits, that's 200 into 10 raised to minus 3 watts. So that's the quantities we are interested in a resistor. In a very quick manner, let me motivate how do you do resistors in parallel. We have about 6 minutes remaining. Resistors in parallel, the electrical circuit looks like this. We have 2 resistors connected in parallel, and the battery itself is connected to the 2 resistors in parallel. That's your voltage V. Let's again say it is 10 volt. That's your resistor R1, and that's your R2. Even before doing anything, exactly like we argued in the case of a capacitor, these 2 points, these are metallic wires. These lines represents wires that you connect to the resistor. These all have the same potential difference because these 2 points have the same potential difference. That's the voltage of the battery. These 2 will have the same because these 2 are the same, and these 2 are the same, and the same with that. And that leads to the idea that V2, the potential difference across the second resistor, and the potential difference across the first resistor, they are all the same. V1, let me write that here. So V1 is equal to V2 is equal to V. They're all connected to the same points of the battery using metallic wires, so they have to have the same potential difference. What about the current? Current I is pulled here, so these are moving charges. Currents are moving charges, so they move around. And once they reach here, if you are a positive charge, there are 5 coulombs of charges going. Some of them have to go here, some of them have to go there, and there is no charge destroyed or created. And in that case, whatever they bifurcate as, the total has to be equal to I. So some of them go here, we don't know how many, and some of them go in through the second resistor, I2. I2 has to go through here, but they have to add up to the current I. So that's your distribution. That current distributes, but the voltage remains the same. Exactly opposite of what we had in our SIUC. Again, have an equivalent resistor and design it as that particular resistor which pulls the same amount of current. So it's the same current that it has to pull, so that I remains the same and the voltage is the same. And that's the definition of an equivalent capacitor. And again, we start with the same equation. That's I1 plus I2 is equal to I. This time, let's again locally replace it with the voltages. So this is V1 over R1. Right? That's your relation for the current I1 plus V2 over R2. That's equal to V over R equivalent. Like whenever it comes to the total, that's the effective resistance we have. But this time the voltages are the same. So voltages cancel and we see that the inverse of the resistances add up to give you the inverse of the equivalent of resistors. And if you remember, that's what happened in the case of capacitors in series. So capacitors in series and resistors in parallel are mathematically equivalent. And again, we can go around calculating each of the voltages and the currents. Always start by calculating the equivalent resistance. And typically what I also do is I give a compound problem where there is an equivalent resistance. So for example, you should be able to calculate the equivalent resistance of a bunch of resistors together. So for example, this is 4 and let's say, so that's 5 resistors in a compound circuit, and I don't ask you to calculate typically the currents that is going through each of the resistor, but I do expect that equivalent resistance you should be able to calculate. That is all we will do for electrical circuits, just circuits, resistors in series, capacitors in series. In the next week, we will start with magnetic field. So all this we have been studying electric field. We will next go to magnetic field. I'll stop here and thank you.